Hi, today on Logic we're going to talk about truth table and logical equivalence. We have three objectives for this lesson. First, we're going to try to recognize if a compound proposition is a tautology or a logical contradiction. Then we'll determine if two compound propositions are logical equivalents. And finally, we're going to construct a truth table for three compound propositions. Let's start with tautology. A compound proposition is a tautology if all the values in its truth table column are true. Basically, a tautology is a statement that is always true. For example, the sentence, if we do not succeed, we run the risk of failure. It's always true because if you do not succeed, it means you fail. If you fail, you run the risk of failure because you're failing. Or, either it will rain tomorrow or it won't rain. This sentence is always true. If it rains tomorrow, this is true. If it doesn't rain tomorrow, it is also true. It covers all possibilities, so it is always true. Let's look at a mathematical example. We ask you to show that P or not P is a tautology. So for this, we're going to construct a truth table. We'll need to look at the value of P, the value of not P, and the value of the disjunction P or not P. P can either take the truth value true or false. Its negation takes the opposite value, false or true. The disjunction is true if we have at least one truth value that is true. So here in both cases, we have one truth value that is true. The last column only has the truth value true, so this is a tautology. Next, we have logical contradiction. A compound proposition is a logical contradiction if all the values in its truth table column are false. Basically, a logical contradiction is a statement that is always false. Example, this is a good example and this is a bad example. It cannot be at the same time a good example and a bad example, so if it's a good example, then it's not a bad example, so this is false, and if it's a bad example, it's not a good example, so this is false. Or, I will pass the math exam and I will fail the math exam. Same thing, you cannot pass and fail at the same time the same exam, so this statement will always be false. Again, let's look at the math example. We want to look at the proposition P and Q and P exclusive disjunction Q and determine whether it's a logical contradiction or not. So first, we need to set up our truth table. First, we're going to look at the conjunction P and Q. Then we'll look at the exclusive disjunction P XOR Q. And finally, we're going to look at the conjunction of these. The conjunction is true only when both of them are true, so we get true and false, false, false. The exclusive disjunction is true only when both values are of different truth values, so we get false, true, true, and false. Now if we do the conjunction of both these propositions, we need to look at the last two columns together and do the conjunction. So in that case, we get false, 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 and false. All the values in the last column are false, so this is a logical contradiction. Next, we have logical equivalence. Two propositions are logically equivalent if they have the same truth table column. As an example, we have shown that not P and Q and not P or not Q are logically equivalent. For this, you can either do one truth table with both compound proposition, or you can do two truth tables and check the last column of each table. So for the first compound proposition, we look at P and Q. We look at the conjunction P and Q, and we look at the negation of the conjunction not P and Q. P and Q is true only for P true and Q true. Everything else is false. Then when we take the negation, we just take the opposite truth values that we had on the third column, which give us false, true, true, and true. For the second compound proposition, we do the same thing with a different truth table. This time we're going to look at not P, we're going to look at not Q, and we're going to look at the disjunction of both. Not P is false, false, true, and true. Not Q is false, true, false, true. If we do the disjunction is false only when there is two false. So if we have at least one true, the disjunction is true. So that gives us false, true, true, and true. Now if we look at the last column of each table, we see that we have the same thing. False, true, true, and true. So we can say that the two compound propositions are logically equivalent. Finally, let's look at how to create truth table for free proposition. First, when we have free proposition, the third proposition we call it R. So we have P, Q, and R. We've seen that for one proposition, the truth table has two rows. For P, either it is true or it is false. That's two rows. When we have two propositions, we have four rows. If we have P and Q, either we have true true, true false, false true, or false false. When we have three propositions, now we get 8 rows. Let's see how we build these 8 rows. So for the first proposition P, this proposition is either true or it is false. For each value of P, the proposition Q is going to take two different values. It can be either true or it can be false. If P is false, it can be true or false. This creates the 4 rows that we have when we have two propositions P and Q. We have true true, true false, false true, and false false. For each value of Q, we're going to have the same thing for R. R can be true or it can be false. Now we have the 8 propositions created by the different value of P, Q, and R. If we write it in a table, it will look like this. Let's see an example of exercise. Construct a truth table for the compound proposition P or Q and R. So first we do the compound proposition inside the bracket P or Q. Then we'll do the conjunction P or Q and R. So we need to set up our truth table with the three proposition P, Q, and R. So we said we do first the bracket, the disjunction, P or Q, and then we have the conjunction P or Q and R. For the disjunction P or Q, we just look at the first two columns, the column of P and the column of Q. This is false only when both of them are false, so we get true, 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 true. Finally, we have a conjunction to do. So for the conjunction, we're going to look at the column 3 and 4. The conjunction is true only when both truth values are at true. So we get true, false, true, and so on. If we look at the last column here, we can notice that it's not a tautology, because not all truth values are true. Also, it's not a logical contradiction, because not all truth values are false. So we say that it is neither a tautology nor a logical contradiction. If you have a question about this, you can write it as neither. Finally, let's see your practice problem. First question, construct the truth table for this compound statement, not P or Q and R. Remember to do the bracket first and then do the disjunction. After you've done your truth table, determine if it is a tautology, a logical contradiction, or neither. Explain why. And finally, find out how many rows should the truth table have for a statement involving 4 different propositions.